Okay, so in the last video we were just at the spot where you were going to use our equation N equals C over V to find the speed of light in both water and in diamond. So in water, and you're going to rearrange this for V equals C over N, and C is the speed of light in a vacuum. It's constant, 2.9979 times 10 to the 8th, and they won't give you that. They'll assume you know it. And then the N, you look on the chart, either in the notes that I uploaded for you or in your textbook on page 397, and you will see that the index of refraction for water is 1.333. And so when you do this, you get 2.24899 times 10 to the 8th meters per second. So that is the speed of light in water. The question also asks you to find it in diamond. And so you do exactly the same thing. C over N, 2.9979 times 10 to the 8th meters per second. Look up diamond in the chart and see that it's 2.42. And when you do this, you get a speed of 1.2388 times 10 to the 8th meters per second. Okay? So there's that equation. It should be pretty quick, easy to use. All right, so now earlier we had said that this N was called the index of refraction. And it was called the index of refraction because depending on the difference in the densities of the two substances, the light, as it passes from one substance to another, is going to refract. It's going to bend at the boundary. Remember, we talked about refraction back when we were first doing our definitions of waves. So refraction is when a light ray comes in, strikes the boundary, and then bends, so that instead of going straight through, because it encounters a different medium, it either speeds up or slows down. And that speeding up or slowing down is going to cause the ray to bend one way or the other. Now, it speeds up or slows down depending on if medium 2 is more dense than medium 1 or less dense than medium 1. The light ray has to be going in, though, at an angle. It can't go straight. If it goes straight in, if it goes in straight in along the normal, it's just going to come straight through. Okay, so it has to go in at some angle other than 90 degrees in order for there to be refraction. And the bigger the difference in the density between the two media, the bigger the bend. Okay, so if we go back and think about, if you remember, we were walking on a beach. Oh, actually, I could do it here at the beach. We were walking on the beach, and the end at an angle, and the end that ended up in the water first trailed behind us. So remember, this ray that I'm drawing is really a ray that's perpendicular to the wave fronts that are coming in. So these are the wave fronts of the light. And so as the lower section here enters the water first, it's either going to travel quicker than the outer one, causing this ray to bend up, or it's going to travel slower than the other one, lagging behind, causing this ray to bend down. So whether it bends up or bends down is totally dependent on, is it going into more dense or less dense? Okay, so if it is going into, let's say this one is less dense. Okay, and I'll do another one for more dense. So if it's going into more dense, then the lower part of this wavefront is going to lag behind, and so it's going to end up traveling this way. And so if we draw our ray, it's going to be down here. Okay, so the angle between my incident ray and my normal, we're going to call theta 1. And the angle between my refracted ray and my normal, I'm going to call theta 2. Theta 1 will be the angle of incidence, just like it was in reflection. And theta 2 will be the angle of refraction. So we're using, oh yeah, I said 1 and I wrote I. We're using 1 and 2 here instead of I and R because the R was already reflection, the R can't also be refraction. That will cause confusion. Okay, so if it's going from less dense to more dense, then it bends towards the normal. LM, it bends towards. Okay, now if we do more dense to less dense, so here's my normal, here's my ray coming in, striking the surface. Okay, so here are the wave fronts, and I'm just drawing these so you can imagine, right? So right at this point, as this edge of the wave front is entering, and this time we're saying more to less, and I should have drawn it upside down because that's how this is, in your book, I started the ray, or in your notes, I started the ray from the bottom. Sorry about that. This one just is the flip of it. So as the lower edge enters the less dense medium, it's now going to be able to travel quicker. And so it's going to move ahead. And so now these light rays, wave fronts will go like this, and my light ray will be up here. So this is my theta I, or theta 1 again, and this is my theta 2. And we say it bends away from the normal. So what we mean by towards is, my camera just flipped around again. What we mean by towards is, instead of it following the straight path down here that it should have, if it was going through without a change in density, it's bent now closer to the normal. And over here, bending away, again, instead of following the straight path, it's bent up away from the normal. So we say more to less, it goes away. Now, the way I actually remember it is, I think of MLA, which happens to be formatting when you're writing an essay. Also happens to be member of the Legislative Assembly if you're into Canadian politics. So MLA, more to less away, and then that allows me to remember that LM must be towards MLT. Okay? So now the good news is there's an equation to help us with this, because clearly how much it bends, what the angle of refraction is going to be dependent on the angle of incidence and the two indices of refraction. And so we get an equation that is called Snell's law. Okay, Snell's law. And the physicist dude was Snell. And Snell's law is N1 sine theta 1 is equal to N2 sine theta 2. So the index of the first medium times the angle of incidence will be equal, sine of the angle of incidence will be equal to the index of the second medium times the angle of refraction. So in your notes there's an example, and the example says it's a ray of light, and it's coming in, traveling from air into water. And the angle of incidence is 40 degrees, and it wants to know what's the angle of refraction. It's going from less to more, so it should be bending down like this. Our answer should be less than 40 degrees, so let's find out. N1 sine theta 1 equals N2 sine theta 2, and you're solving for sine theta 2. So N1 sine theta 1 over N2. You use your chart to find the index for air and the index for water. The index for air is 1.00029 sine of 40 over 1.333. Okay? What you're going to get is sine theta 1. It works out to be 0.048235. In case you're wondering where the heck I came up with these two numbers, I looked on the chart for indices, okay? Once I get to here, I do inverse sine of both sides, and I get my theta 1 to be 28.839. Oops, sorry, except it's really theta 2. It morphed into a 1 when I went from there to there. Okay, so my index of refraction is 28.839 less than 40. It is, and so it should be bending towards. Okay, so today you're going to practice with this equation. Oh, and notice how close air is to a vacuum as we